Welcome to the lecture video for Math 1, page 32. The first topic we'll talk about today is how you can use an x and y intercept to find the slope of a straight line. We've talked quite a bit about finding x and y intercepts. Remember, the easiest way to do that, let's take the example 3x plus y equals 6. To find the y-intercept, for any y-intercept, the x value has to be 0. Y-intercept is obviously talking about when it crosses this line, and any place on this line, x has to be 0. So if you just plug in 0 for x, 3 times 0 plus y equals 6. Solve that for y. Clearly we will just get y equals 6. Not too tough. So that's going to be at the point 0, 6. We can find the the x-intercept in the same way, because when I'm looking for the x-intercept, I'm looking for a point along this line, but at every point along that line, y has to be 0. Because remember, y is by definition the distance from the x-axis. So I can just come back up here, plug in 0 for y, 3x plus 0 equals 6. Solve this guy for x, dividing both sides by 3, and I'll find out that the x-intercept is 2. We've got a nice little line there, which is at 2, 0. And then once you've got the two intercepts, obviously the straight line is going to go through both like so, more or less. And the slope is always the change in y over the change in x. But since you've got these nice points to work with, 0, 6, and 2, 0, the change in y is just going to be 6 minus 0, or 6. And the change in x is going to be 0 minus 2. So be careful, that would be a negative 2. So in this case, our slope should be negative 3. Well, if you look at that carefully, one way to find the slope is always going to be the y-intercept. A little note down here. The slope is going to equal the y-intercept divided by the x-intercept. But not quite. We're going to need to make a little fix here, aren't we? Because if the y-intercept is 6 and the x-intercept is 2, 6 divided by 2 is going to give us a positive 3. Obviously, we need to use a negative 3. So it looks like a shortcut to find the slope is simply the negative of the y-intercept divided by the x-intercept. Let's think about that for a second. What if we had a different graph down here where the y-intercept was a positive value here and the x-intercept was a negative value? Clearly the y-intercept is positive, the x-intercept is negative, but the slope through these is clearly going to be positive. So it looks like that's an important correction to make. We just include this little negative sign here. We can always find the slope of a line by taking the negative of the y-intercept divided by the x-intercept. There's at least one problem on page 32 that'll be helpful for. The next thing I want to talk about is collinear versus parallel. And what is the difference between those two ideas? These blue points appear to be collinear. That's because if I draw a line through them, they will all be on that line. They are collinear. They're all on the same line. Notice that is different from the idea of parallel. Because these points here, obviously also collinear. Remember, any 2 points have to be collinear. In fact, 2 points define what a line would look like. But this blue line and the red line are parallel. Clearly that is not the same as collinear. All 5 of these points are not collinear. The reason to be very careful here is if I simply gave you these 4 points and you found the slope between these guys and the slope between these, they would all have the same slope. But they would not be collinear. So you have to be very careful. You would not want to say that all 4 of these points are collinear. Connecting these has the same slope as these, but they're obviously not on the same line. If you have 3 points and want to show these 3 points collinear, there's a bunch of ways to do it. You could find the slope between these and the slope between these, and you're okay because you've used this same point for both of them. But an easier thing would probably be to find the slope between these 2 points and then find the equation of that line and verify that this point is also on the line. Just be careful. Parallel is not the same thing as collinear, and make sure you prove it on homeworks and assessments. Final thing I want to talk about, kind of a big topic that we'll talk about quite a bit as we move into geometry, algebra 2, and precalculus, is the shifting of functions left or right. And we can do this with an example of y equals the absolute value of x. I think we know enough by now to realize the graph of the absolute value of x is just this sort of V shape. Well, I want to see what happens. I'm going to come up with two new functions. Y equals the absolute value of x minus 2, and y equals the absolute value of x plus 3. Now let's just make a little data table here and see if we figure out what these might look like. So I've put in some x possibilities, and we're going to figure out what the y is to go along with it. If x is 4, 4 minus 2 is 2. Absolute value of 2 is clearly 2. If I plug in 2, 2 minus 2 is 0. Absolute value of 0 is 0. Now I've got 0 minus 2. That's a negative 2, but the absolute value of negative 2 is 2. Check out some negative values. If x is negative 1, negative 1 minus 2 is negative 3. Absolute value of that is 3. If x is negative 5, negative 5 minus 2 is negative 7. Absolute value of that is 7. I'm just going to plot some of these points. So 4, 2, 1, 2, 3, 4, going up 2 right about there. When x is 2, I'm at 0. When x is 0, I'm up to 2. At negative 1, I'm at 3. At negative 5, I'm at 7. And I'm pretty sure it looks like if I did these for a long time, I got lots of dots, it's going to look like this. Interesting. Let's do the same for the absolute value of x plus 3. Let's do 4. 4 plus 3 is 7. Absolute value of 7 is 7. 2 and 3 is 5. Absolute value is 5. 0 and 3 is 3. Absolute value is 3. Negative 1 plus 3 is 2. Absolute value of that's going to be 2. Negative 5 plus 3 is negative 2, so that's also going to be 2. A little more interesting here. So now when x is 0, I'm up here at 3. Let's do the rest. When x is 4, now I'm up here at 7. At 2, I'm around 5. At negative 1, I'm at 2. At negative 5, I'm also at 2. And it definitely looks like that if I included another point here, if I put my x of negative 3, negative 3 plus 3 is going to be 0. So that's what's going to put me down on the x-axis when I'm here at negative 3. So if I graph these out, it looks like I've got something along these lines. You have to come back and look at these graphs pretty carefully. It appears that making this x minus 2 took my graph and shifted it over 2 to the right. And if you look very carefully, that's all we've done. This appears to have shifted right by 2. And if I look at the green graph, the absolute value of x plus 3, and this was 0, 0, this is over here at negative 3, 0, and it actually appears that all of the points on the original absolute value of x graph have just shifted left by 3. There may be some hints inside the functions here that tell us exactly how we could have graphed that without going through the table. Keep that in the back of your head. We'll talk about it more soon and have a good time with problems on page 32.